In section 4.4, we'll be studying the properties of logarithms. This section is broken down into two different pieces. In part A, we'll be looking at law of logarithms. These properties will allow us to solve logarithmic and exponential equations. These properties are algebraic in nature and have a very nice symmetry to them. Then in part B, we'll be looking at change of base. Change of base is going to be used as a computational tool that will allow us to compute logarithms with strange bases in terms of logarithms with bases that we know how to compute. Let's go ahead and look at part A. To begin, we'll go ahead and list the law of logarithms. Let a be larger than 0, and let a not be equal to 1. Also assume that capital A, capital B, and capital C are any real numbers where we have that a and b are strictly greater than 0. Then we have the following three properties. 1. The log base a of a times b is going to be equal to the log base a of a plus the log base a of b. 2. The log base a of a divided by b is going to be equal to the difference in logs, which is the log of a minus the log base a of b. Then the third property, the log base a of a raised to the c is going to be equal to c times the log base a evaluated at a. Let's go ahead and prove this. First, let's go ahead and assume that the log base a of large A is equal to u, and we also know that the log base a of b is equal to v. Writing this equivalently as an exponential, this is going to be a is equal to a raised to the u, and b is equal to a raised to the v. Now that we have this relation here, let's go ahead and prove part 1. The log base a of a times b is equal to the log base a of au times av. By properties of exponentials, this is equal to the log base a of a u plus v. Since the log and exponentials are inverses of each other, this is equal to u plus v. Then we know that u and v are given by these functions up here, which means that we can rewrite this as the log base a of a plus the log base b of b. For number 2, we start off with the log base a of a divided by b. This is going to be equivalent to the log base a of a times b raised to the negative 1. By part 1, this is equal to the log of a evaluated at a plus the log of a evaluated at b inverse. Replacing b inverse in the previous equation, we rewrite this as the following. Again, in this term here, since the log of a evaluated at a raised to some number are inverses of each other, we see that this is going to then be equal to the log base a evaluated at a minus v. V, again, from this upper piece we know is the log base a evaluated at b. So we get that this is equal to the log of a evaluated at a minus the log of a evaluated at b. So that's the end of number 2. Let's go ahead and look at number 3. We start off with the log base a of a raised to the c. This is equivalent to the log base a of a raised to the u raised to the c. Again, the log and the exponential are inverses of each other. So this is equal to log base a of a raised to the uc. And as I just said, the log base a and the exponential cancel each other out, and we're left with that this is going to be u times c. This is equivalent to c log base a of a. And that's the end of our proof. Let's go ahead and use these properties to evaluate some logarithms. Here we have 3 different logarithms that we want to evaluate using our logarithmic properties. We'll go ahead and start with part A. Here we notice that we have log base 5 and 5 raised to some power, as the square root is the same thing as raising something to the 1/2 power. Rewriting this as the log of base 5 of 5 raised to the 1/2, we can go ahead and use our property of canceling out the logarithm and the exponential and leaving just the exponent, which is going to leave us with 1/2. In part B, we see that we have a natural log of e raised to some exponential, so we can go ahead and use the property of logarithms that allows us to bring the exponential down in front. This is then going to be equivalent to the natural log of e raised to the 2000 times the natural log of e. Since the natural log of e and e itself are inverses of each other, again, this is equal to 1. So this is going to be equal to the natural log of e raised to the 2000 times the number 1. All right. Again, we can use the exponential, we can use the property of the log to bring the exponential out in front, which means that this is equal to 2000 times the natural log of e times 1. Here we see that from the properties of logarithms, this is equal to 1, and we're left with 2000 times 1 times 1, which is just 2000. Then, in this last part over here, we want to notice that 16 is 4 raised to the 2nd power, so that we can rewrite this in terms of the base 4. We get that this is going to be equal to the log base 4 of 4 squared raised to the 10th. Simplifying this using exponentials, this is equal to log base 4 of 4 raised to the 20. Using our properties of log, again, we can take this exponential and bring it out in front, which gives us 20 log base 4 of 4. Here, we see that this simplifies to be just 20.